Hello viewers, welcome to another session of All Force e-learning program. In this episode, we shall now take up the applications of the charge distribution, continuous charge distribution. The analytical approach to this, we shall take up the applications of it. Applications of the continuous charge distribution. Till date, we were talking about the point charges. We were considering point isolated separate charge, a single charge at a point. In the sense, mathematically, the size of the charge is negligible when compared to the distance of the point of concentration. Such charges we were dealing. First we considered point charge. Later we took the combination of two equal and opposite charges called dipole, the effect of it, electric field, all that. Many charges, multiple charges, again discrete, separate, isolated charges, point charges, sum of all. Now let us take up the applications of the charge when charge is continuously distributed. For example, imagine suppose a charge is distributed over a wire like this, charged wire. Charge is spread over a wire this way, linearly like this. Charge linearly it is distributed, uniformly it is distributed. So a question is given like this. A thin glass rod is charged uniformly with charge density, linear charge density lambda naught. If its length, the length is L, the amount of charge contained on it, the total charge that is possessed on it. So we know according to the definition of linear charge density, charge is Q by L. Since it is uniformly charged in the sense lambda is constant Q naught. Let the charge possessed by it is capital Q, length L. So cross multiplying, Q is equal to lambda naught into L. So the charge contained by the rod, thin rod of length L, so lambda naught linear charge density, which is a constant, into length. It is directly proportional to length. So Q proportional to L. So in the sense Q1 by Q2 is L1 by L2. More the length, more the charge possessed by it. Right? So therefore Q proportional to L. Linear charge, line of charge, whatever length it possesses, according to that we will consider thing. This is for a linear charge where the charge is uniformly distributed. Then lambda is like this. Now what if the charge is not uniformly distributed? In the sense, same rod, a same glass rod, let's say of length L, right? Same length L like this. Charge is distributed, but the charge distribution is not uniform. Right? At one place it is less, at another place it is more. Charge is not uniform, right, like this. Then if the charge accumulation is not uniform, it is varying, then how do you find? Let's suppose it is given as the linear charge density of the rod is lambda naught into x from one end O, where x is the distance from one end O. Length of the rod is L. Length of the rod is L. Its linear charge distribution lambda, linear charge density lambda is lambda naught into x. In the sense, let us understand. Put x0. So at this end, x0. So this is 0. So there is no charge at that end. Put x equal to 1. Let's say centimeter, 1 centimeter. So lambda is lambda naught. At 1 centimeter distance, the amount of charge is lambda naught. Put x equal to 2, it's 2 lambda naught. Within the same centimeter, there is double the charge. Next 3 lambda naught. So as you move on, the charge accumulated is increasing. Right, the density is increasing. It's not uniform. So here it is less, but as you move away, more charge is accumulated as you move away like this. In such case, how do you find the charge? Now the question is, what is the total charge possessed by the rod? The total charge contained by the rod is dash. So this is the question. Now in such cases, how do you do the problem? Now, for all such problems, what we have to do is, we have to perform integration. You know, we have studied in your first year in basic maths, whenever there is a physical quantity varying It's not a constant, varying with respect to another physical quantity. There is a variation, an expression which shows variation of one physical quantity with the other. Then we are asked to find out the product of it. Then we calculate the thing by integration. Now how? What shall we do is, consider a small element, length element over this glass rod. Take a small length element dx, very small, dx, right? So let the charge possessed in this length element be dq. Now at this point, and let this element be at a distance x from this end, x from the end from where it is x being defined, right? So consider a small length element, like suppose if I consider a stick like this way, then over this out of all the, let's suppose this is the rod, charge is being distributed, then let me consider a length element of this width of this band, this rubber band, right? Small length element like this. Over this length, over this end to this end, the lambda variation is negligible. We can consider lambda to be a constant over that element. So over that element I can consider lambda to be constant. So lambda is lambda naught x. So let this element be at a distance x from the end where this x is defined in the expression, in the problem. In the problem we are given lambda is lambda naught x, where x is the distance measured from one of the end O. So from that end O, I am taking the length element at x. Dx is the length dq at a distance x. Then, so here if I define linear charge density, we know according to the definition, linear charge density is the amount of charge per unit length, charge possessed per unit length. So over this element, we are now talking about only this element. Forget about the rod there. Let's take up only this element. Over this element, the length is dx and the charge is dq. So according to the definition of linear charge density, it is the amount of the charge possessed per length, unit length. So the charge is dq over that element dx, length element. So lambda is equal to dq by dx. Please cross multiply. So I get dq is equal to lambda dx. This is the charge. So this is the small amount of charge that is contained in small length element, small element of length, that is dx. Within that length, the charge dq, it is mathematically defined as lambda into dx. And we know this is at a distance x. So we are given in the problem with the expression lambda is lambda naught x. Please substitute here. So therefore, I get dq is equal to lambda naught x dx. So the charge contained, small charge that is contained in this element dq, it is equal to lambda naught, where x is the distance of that element, into dx. Dx is the length of that element. Now I can define such elements, length elements here, over the length of the wire from this end to this end. Let's say this is O, this end is A. From O to A, I can consider such small tiny elements dx of same length. Let the charge contained in them be dq1, dq2, dq3, dq4, dqn. Then what is the total charge? The sum of all the charges. So the total charge contained by that rod is sum of all the tiny elementary charges dq1, dq2, dq3, dq4, dqn, the total sum of all the tiny elementary charges. Now this mathematically I can define it as integral dq. According to mathematics, what is the total value? Sigma, sum of all the elementary values. So the total is sum of all, right? Integration of dq. So substituting this here, so I get q is integral of dq, that is lambda naught x dx. But charge from where to where? From point O to point A. So what are the limits? O to A. Mathematically the limits are O is x0 and A is xl. So the length, mathematically the limits are 0 to L. So the charge Q is equal to integral of, this is integration, in mathematics, integration, it is summation of all the tiny elements, sum of all the elementary values, summing up all the elementary values, total value is Q. So it is integral of dq we have defined it as lambda naught into x. We have got it from this, lambda is dq by dx. Whenever you come across such non-uniform charge distribution, you have to apply this case. Consider a small element dx, where the charge on it is dq. Let the small charge possessed by dq, and it is at a distance x from the end where x is being defined, right, in the problem that is given. So therefore, according to the definition, linear charge density is charge per unit length. That small charge possessed in that small element, that is dx, dq by dx, cross multiply, dq is lambda dx. But lambda in the problem it is given as lambda is lambda naught x, substitute lambda naught x. So therefore, q is equal to dq, substituting this in this, so dq I get this. But integrating over a limit, what are the limits? I want the charge possessed by the rod of length L extending from O to A. So diagram wise it is O to A. Mathematically from x0 to xl, like this. Now in this one, lambda naught is a constant. Take this out. So q is equal to lambda naught integral 0 to L x power 1 dx. This is x power 1, given it is x power 1. He can give you x power 2, x power 3, anything. We know, according to the integration, we have got a formula, x power n dx. According to mathematics, x power n dx, it is x to the power of n plus 1 by n plus 1. Integration formula. You have studied this in your first year. X power n dx is equal to x power n plus 1 by n plus 1. If the limits are x1 to x2, the integration is x power n plus 1 by n plus 1 from x1 to x2. Then how do you evaluate? Then upper limit minus lower limit. It is x2 power n plus 1 by n plus 1 minus the lower limit x1 power n plus 1 by n plus 1. So this is the integration. So substituting here, same, performing the same here. It's lambda naught x power, it is 1. So here in this formula x power n, so integration we get x power n plus 1, that is x power 1, we get 1 plus 1 by 1 plus 1. Between the limits x1 to x2, here the limits are 0 to L, so it is 0 to L. So therefore, I get, so q is equal to, q is lambda naught into x power 1 plus 1, 2 by 1 plus 1, 2. So it's x squared by 2 between the limits 0 to L. Now substituting the upper limit minus lower limit. So q is equal to lambda naught into, it is L square by 2. L square by 2 into between the limits 0 to the upper end like this. Is it? So 0 is the lower limit, upper limit is lambda. The upper limit lambda square by 2 minus 0 square by 2. So q I get it as lambda naught L square by 2. This is the formula for charge. The formula for charge is lambda naught L square by 2, where L is the length of the rod. Lambda naught is the constant k that is given. Right? It can be k, or here in this problem he has given it as lambda naught. So it's lambda naught L square by 2. This is the charge possessed by the rod for non-uniform charge distribution. Right? Whenever the charge is distributed in a non-uniform manner, then we should consider the charge to be like this. If suppose a linear charge, if I consider another linear charge, let's say charged ring, charge is being distributed over a ring, then for a ring the linear charge density, if charge is distributed over a ring uniformly, 1 minute, charge distributed over a ring uniformly over a ring, there is a charged ring of radius r where the charge is uniformly distributed over a ring like this. This way, all the circumference of the charge, all the circumference of the ring, the charge is uniformly distributed. Let its linear charge density be lambda. Now the question, what is the charge possessed by the ring? What is the charge contained over the ring? We know according to the definition, linear charge density lambda is charge per unit length. Now cross multiply. So the charge contained is lambda into length. Now what is the length? Suppose if I consider from this end, the total length of the ring, circumference of the ring, the total circumference, charge is distributed over a total length. The total length over which the charge is distributed from this end throughout this, it is the total circumference. So L is 2 pi r. The length over which charge distributed completely over the length, the total length of the ring L is 2 pi r. So Q is equal to lambda into the length is 2 pi r. So the total charge possessed by the ring, charged ring, is 2 pi lambda r, where lambda is the linear charge density of the ring, where the charge is uniformly distributed, lambda is a constant, then charge possessed 2 pi lambda into r. This is the charge possessed. If it is linearly uniformly distributed, then Q is 2 pi lambda into r. Okay. Now suppose if I take another application. Now the charge distributed over a sheet, plain sheet. For example, suppose a charge is distributed over a square plate of side A. Uniformly charge being distributed over a square plate like this. Then for uniform charge distribution of charge over a plane, right, over square plate, a glass plate, charge is being distributed uniformly. Let the surface charge density of this plate be sigma naught. Then now the question is, what is the charge contained by the square plate? We have defined surface charge density is the amount of charge contained by the sheet per unit area. The amount of charge contained by sheet per unit area. So sigma is naught is equal to Q by A. Now here the charge is contained only on one side. Charge is not distributed on either side. It's only on one side. Then sigma is equal to Q by A. Cross multiplying. The charge possessed is sigma naught into A. Where the side of the square, it is a square of side A. Even this is A, this is A. Area of the square, we know it is A square. So therefore the charge possessed is sigma naught A square. Right? Here it is a non-conducting sheet where the charge is accumulated only on one side. So if it is only on one side, then the charge possessed sigma is Q naught, sigma naught A square. If it is a conducting sheet where the charge is accumulated over this side on either sides, then the total charge would be charge here plus there is charge here. If it is a conducting sheet, then the answer will be twice this. I have considered a non-conducting sheet where the charge is only on one side. Then the answer Q is sigma naught A square. Had it been a conducting sheet with both sides charge, whenever you give charge to a conducting sheet, charge is spread throughout the space, open space, this side as well as this. Then the charge will be on this plane, on this surface. Twice it is for a conducting sheet. But I consider it as a non-conducting sheet, then it will be of this. Similarly, had it been a rectangle, instead of area L into B, you consider, right, you should take L into B. If it is a charged disk, sigma Q by pi r square. If it is a disk of radius r, then the area of the disk is pi r square. Then sigma will be Q by pi r square. Again non-conducting, Q by conducting, twice it is, 2 times like this. A special question, a different question. There is a sphere, a hollow spherical shell. There is a spherical shell, hollow, where the charge is distributed over its surface uniformly like this. If the charge distribution is uniformly, right, of radius r, Q it is, then what is the charge possessed by this spherical shell? Whenever a sphere, a conducting sphere or a non-conducting sphere, spherical shell, even if it is a conducting solid sphere also, whenever you give charge to a conducting solid sphere, no charge will be deposited inside the sphere. For a conductor, there is no charge inside. All the charge will be accumulated on the surface only. All charge appears on the surface only, right? So it behaves as a spherical shell, charged spherical shell. For a non-conducting hollow sphere, non-conducting spherical shell, charged sphere, then for this, the surface charge density sigma is Q by A. So sigma is Q by the surface area of a sphere, it is 4 pi r square. The surface charge density of a spherical shell, charged spherical shell, or it is a conducting sphere, charged conducting sphere also it is the same. So what is the charge Q? Cross multiply. It is 4 pi sigma r square. Now from this, suppose if charge is constant, then sigma inversely proportional to r square. Right? Charge is constant, sigma inversely proportional to r square. Or if sigma is constant from this, if sigma is constant, then charge directly proportional to r square. Q proportional to r square. If sigma is constant, then Q proportional to r square. Now if charge is constant, Q inversely proportional. Taking the ratio sigma 1 by sigma 2, first sphere, a small sphere, sigma 1, it's Q1 by 4 pi R1 square. Sigma 2, it's Q2 by 4 pi R2 square. So 4 pi cancel. I get Q1 by Q2 into R2 square by R1 square. So this will be sigma 1 by sigma 2. Two spheres, when I compare two spheres of surface charge density sigma 1, sigma 2, charge Q1, Q2, radius R1, R2. Then, suppose if charge is same charge is given to two different spheres, then the surface charge density ratio is R2 square by R1 square. No, same surface charge density, two different size, sigma same, Q1 by Q2, R1 square by R2 square we get when you cross multiply. Right? So for hollow spherical shell, hollow spherical conducting sphere or non-conducting hollow sphere, spherical shell, the surface charge density is Q by A, it is Q by 4 pi r square. Right? Now, here it is a uniform sphere. For a uniform sphere, it is in this form. Suppose if it is a non-uniform sphere, based on this, there was a previous entrance question, so I am putting it keenly, just understand. When it is a hollow uniform sphere, a perfect sphere, then charge is spread uniformly. In a conducting sphere, charge is uniform. Then sigma will be Q by epsilon 4 pi r square. Now, if it is a non-uniform sphere, for example, let us say an egg-like thing, egg-shaped, oval-shaped or egg-shaped thing, right? Let's say the sphere is something like this, a curved. It's not a sphere, a curve of this shape. Charge is given to it. Then now suppose surface charge density at this place, let us say A, sigma A, this is A, this surface is A, let this surface be B, so here it is sigma B and this surface is C, let this be sigma C. Then there was a beautiful question asked in 2012 in one of the national entrance examination. If charge is given to a non-uniform sphere like this, egg-shaped conductor, right? Then the charge is being distributed like this way. Then he is asking you the inequality between these three surface charge densities. The inequality relation, the inequality between these three surface charge densities. Now please consider, when I take up this C, here the curvature is more curved, a steep curve. You know, whenever the curvature is steep, curve is more, the radius is less. You know, surface charge density varies. I was just now telling you, it's 4 pi r square. When charge constant, surface charge density varies inversely proportional to r square. When it is a steep curve here, sharp curve, then radius is less. If radius is less, surface charge density is more. Sigma is more, this is small. So this will be maximum, high. right? So here the curvature is more. When curvature is more, curve more, bent more. So when you have to bend more, when you bend more, the radius is less. When curvature is more, radius is less. Radius less, sigma more. Now coming to B, here a bit curvature, a bit lesser than this, but more than this. Right? So here it is moderate. Even this is also moderate. Coming to this surface, here the curvature is very much less. So the radius is less, sigma will be, radius is more. Curvature is less, radius is more. Curve is less, radius more. A less bent curve, if you have to complete, the radius will be more. So therefore radius is more, sigma less. So sigma A is less than sigma B, less than sigma C. So therefore it is A less surface charge density, because the curve, it is less curved. Curve less, radius more. When radius is more, sigma is less. See here curvature, curve is more, steep curve. Radius is less, sigma is more. That is what? A very beautiful question asked in previous entrance examination. Very recent mistake. Now coming to another application of this surface charge density. When you look upon a very big huge building, you find some steep, thin conductor called lightning conductor. You know, a lightning conductor is made up of a thin, sharp edge like this. The principle involved in putting it is sigma is q by 4 pi r square. Right? So therefore radius, it is a sharp edge. Radius is less, surface charge density is more. More surface charge density is accumulated. Actually, for any such curved thing, surface charge electric field intensity strength depends on sigma. So more field is accumulated, more field, strong field is produced. Now which produces high potential. As such, when there is a lightning taking place, now when a cloud reaches over the top there, now there is a potential drop between these both, which decreases the potential drop. An electric wind is produced. Because of the electric wind, there is a potential drop, and even if there is a lightning, all the charge will be accumulated, will be directly sent to the ground. Even if there is lightning above a building, then the charge, whatever that is accumulated, directly is taken into the earth by the lightning conductor because of its sharp edge. Edge being sharp, radius is less, more surface charge density, more strong field, more charge is accumulated, more strong field is produced. Because of strong field, high potential is produced, which reduces the potential between the cloud and the edge of the conductor. As such, all the charge is sucked in. An electric wind is produced, which will reduce the which will connect both, and which will directly take the charge. All the charge directly is taken by the conductor into the earth. So the principle, that is the basic principle of a lightning conductor. It is put with a sharp edge, because at the sharp ends radius is less, surface charge density is more charge is there. So third one, consider a sphere of radius r. A charge being distributed over it uniformly over the sphere. Charge Q amount of charge is being distributed over it, over the volume, complete volume inside. Then what is the volume charge density? The volume charge density rho is equal to charge per unit volume. So rho is Q by 4 pi r, 4 by 3 pi r cube. Volume of a sphere, we know it is 4 by 3 pi r cube. So rho is Q by 4 by 3 pi r. The total charge in the sphere is rho into 4 by 3 pi r cube. Sometimes you need to find out only, suppose if I consider only a sphere in it of radius small r. Sometimes you need to find like this. If I have to take only this volume of this sphere of radius small r, then what is the charge? Then if I take the volume of radius only small r, then the volume considered is 4 by 3 pi small r cube. Then rho is small q by 4 by 3 pi small r cube. So small q is 4 by 3 pi small r cube into rho. But capital Q is the total charge distributed over the total volume. That is, capital Q is for the total volume 4 by 3 pi r cube. Then capital Q is equal to 4 by 3 pi capital R cube rho. So in this sphere, if the whole charge, the total charge distributed in the total volume is capital Q, then what is the charge contained in this small sphere of radius small? The question is, what is the charge contained in the small sphere of small? Then divide 4 by 3 pi, this cancel, this cancel. Small q by capital Q is r cube by r cube, or small q is capital Q by r whole cube. A very beautiful thing which is required. Sometimes you come across such derivations you need to find the charge contained in the inner sphere. For capital R complete radius, charge is capital Q. For small r inside the sphere, what is the charge possessed? It's capital Q times small r by capital R whole cube. Right? So this way we find out the things. Thank you.